Hello everyone and welcome back to the hellgeekarena, and today we are here to discuss about another very interesting problem on Leetcode, which is the course schedule. Now this problem is very interesting because it deals with some of the very important concepts of directed acyclic graph and topological sorting. So let's take a look at the problem. So basically in this problem, you have been given a total n number of courses which have been labeled with an ID starting from 0 to n minus 1. And then besides that, you have been given a prerequisites array. Now each element in this prerequisite array is basically a pair, which denotes that for understanding a particular course of ID X, you should have a pre-knowledge of ID Y. For example, a pair 0, 1 indicates that to take up course 0, you have to first take up course 1, right? So you have been given that if you want to study course X, you should know about course Y, and these kind of prerequisite pairs are given to you along with the number of courses. At the end of it, you need to answer us that what is the order in which you should take up these courses so that all these prerequisites are fulfilled. Now you might also fall into a pit wherein it might happen that it's not even possible to take up all the courses. What can happen is, let's say the prerequisites array contains two elements into it. One pair is 0, 1 and another pair is 1, 0. Now this indicates that to take up course 0, you should know about course 1, and to know and to study course 1, you should know about course 0. So basically there is a cyclic dependency of 0 between 0 and 1. That is, to study 0 you should know 1, and to study 1 you should know 0, which is not possible. So in that case, you cannot answer such a problem, and you need to return back an empty array. So let's take a look at how we can solve this problem. So before we jump into the detailed solution of this, let's first try to understand some of the important aspects that are associated with this problem. Now the first one is directed acyclic graph. Now what a directed acyclic graph is, basically let's try to understand each of the term one by one. The directed over here means that all the edges that are present in the graph have a unidirection, that is, they are not bidirectional. Now if you see this particular graph, all the edges, that is, let's say an edge going from 5 to 0, right, it has a specific direction to it. It is not bidirectional, right? It has a direction from 5 to 0, but and also, like, if you see an edge coming from 5 to 2, then 2 to 3, so all these edges are kind of unidirectional. There is no bidirectional edge in it, so such a graph is called a directed graph. Now what acyclic means is basically that in the directed graph there are no cycles, right? Then it is called a directed acyclic graph. Now if you see this entire graph, there are no cycles present in it. Like if you start from 5, you cannot reach back to 5. Like you go to 2, you go to 3, you go to 1, but you cannot go to 4 or 0 or back to 5. And similarly, if you start from any other node, let's say from 4, you can go to 0 and 1, but you cannot somehow get back to 4. So if you are starting from a particular node, you cannot get back to that node, then it is called a acyclic graph. So basically a directed acyclic graph means all the edges present in that graph are directed, have a unidirectional, they are not bidirectional. And second property is there are no cycles present in the graph. If a graph follows these two properties, it is called a DAG, that is a directed acyclic graph. The short form of it is DAG, which is pretty commonly used, right? So why I'm talking about directed acyclic graph for this problem is because if you see the problem statement, it says that some of the subjects are dependent, some of the courses are dependent upon other courses, right? But in case it happens that so that means that there are edges from one course to other. But in case it happens that, let's say there is a dependency between course 0 to 1, and there is also a dependency between 1 to 0, then that means there is a cycle present. It's not a DAG, right? And if it is not a DAG, then that means for this particular problem the solution is not possible, right? You need to return an empty array. So basically a solution would be possible for this problem only if the graph that has been given to you is a DAG. Now let's move on to some of other concepts as well. Now DFS, that is depth first search, is something that we already know about, but I would just like to superficially touch it again. just as a point of revision. So basically there are two important things associated with a DFS. One is a solution set, another is a visited set. How we traverse in a DFS is like we can start from any of the node. Let's say we start from numbering from 0 to n. So we are going to start traversing this graph from 0. So let's say we start from 0, we put it into our visited set, we check is there any other node connected to 0, that is there any other outgoing edge coming from 0? No, there are no edges coming. So yeah, we have added it to our solution set and visited set, but there are no other edges. So we are going to move to the next node, which is 1. So we are going to put 1 into our visited set, we are going to put 1 into our solution set, and we are going to see are there any other outgoing edges from coming out from 1? No, there are no other outgoing edges coming out from 1. So we are going to move to the next node, which is 2. So 2 we are going to put into our visited set, and 2 we are going to put into our solution set. Now why we are maintaining the visited set? So just to check that we are not revisiting any other element again which we have already visited. So let's say if we would have got 1 again, then we wouldn't visit 1 again, because we have already visited it and we have already covered all its children. So from 2 we see that what are the different nodes that are connected to 2. Now we see that 3 is connected to 2. Right, so we are going to move to 3. So 3 we are going to add to our visited set, 3 we are going to add to our solution set, and we are going to see are there any other edges coming out from 3? Yes, 1 is connected to 3. So what we are going to do is that we will try to visit 1, but we see that 1 is already something that we have visited, so we are not going to revisit 1, right? So we are not going to revisit 1. Now we are going to move to our next element. Why we are going to move to our next element? There are no more outgoing edges from 3 or from 2, because we have already visited all the other outgoing edges. So we have completed this particular subgraph. So we are going to move to the next part, which is like 4. So 4 is not visited as yet, so we are going to visit it now. We are going to mark 4. We are going to mark 4 into our solution set as well. Now we are going to see are there any edges coming out from 4? Yes, 0 is connected to 4 and 1 is also connected to 4. So we try to visit 0, but we see that 0 is something we have already visited. So are we going to visit it? No. Now next node we try to visit is 1. 1 again we see that 1 is something we have already visited it. So we are not going to visit it again. Right, so now we have completely covered the this particular subgraph coming out from 4. So we are going to move to the next node, which is 5. Right, so we see are there any edges coming out from 5? Yes, 0 is connected to 5, and let's say 2 is also connected to 5, but we see that both 2 and 0 is something that we have already visited. So we are not going to visit 0 and 2 again, and we are just going to add 5 into our visited set and solution set, and we are going to move out. And we see that all the elements that are present over here we have already visited, and here comes our solution set, which indicates that the order in which we visited all the elements. Right, now let's move on to the next section. Now we are going to talk about topological sorting, which is also defines a particular order in which we should traverse the element while doing a DFS. So this is kind of a special case of a DFS where we define a special sort of an ordering of elements in which we visit during the DFS. So topological, according to the definition of topological sorting, topological sorting for a DAG is a linear ordering of vertices such that for every directed edge u comma v, vertex u comes before v in ordering. Right, what does it mean? That if there is a directed edge from u to v, then u should come before v in the final solution set. Like if there is an edge from 5 to 2, then 5 should come before 2 in the order set. If we see the previous solution, in this there was an edge from 5 to 0 and there was an edge from 5 to 2, but if you see 5 comes after 0 and 2 in the final solution set. So this is not a particular topological sorting order. This is a particular representation of a graph, but this is not a topological sorting order, because 5 is coming after 0 and 2, but there is an edge from 5 to 2 and 5 to 0. So this is not a topological sorting order. So according to topological sorting order, the linear ordering should be such that if there is an edge from x to y, x should come before y. And also there is one important case of topological sorting. Topological sorting for a graph is not possible if the graph is not a DAG. Now why do we say that it is not possible? Because let's say if there would have been an edge from 0 to 1 and there would have been edge from 1 to 0, then how can we define the topological ordering? Because the primary condition for topological ordering is that if there is an edge from u to v, then u should come before v. So in this case what will happen is that 0 should come before 1 and 1 should come before 0, which is not a possibility. So for a DAG to have a topological sorting order, it should be basically, for a graph to have a topological sorting order, it should be a DAG. It should be a directed acyclic graph. There shouldn't be any cycles in it. Right. So basically this defines our topological sorting. Now why we talked about topological sorting over here is because if we see our current problem statement, what we want to do in it is basically we want to define a particular ordering in which we should study those subjects. That is if like let's say 0 is dependent upon 1 and 2 is dependent upon 3, and let's say subject 5 is dependent upon 6, then the topological one of the intended topological sorting order could be 0, 1, 2, 3, 5 and 6, right? We cannot study 1 before 0, right? So basically that's why topological sorting would come handy into this problem statement, because what we need is basically we have been given kind of a dependency upon courses between each other, and what we want to find out is basically the order in which we should study those courses. That's why topological sorting is something that will come handy into solving this problem. So let's take an example and try to see how we can do topological sorting. So let's take the example which we have been talking about since this entire discussion. So let's start. So basically there are two basic ingredients or components of topological sorting. One is a stack. So stack, as we would already be knowing, is basically a LIFO structure that is last in first out. Whatever element is at the top or has been added last is the first one to be taken out. And the second component of topological sorting is basically a visited array, which is same as the one we had for our basically DFS. So if we see the difference between DFS and topological sorting is basically in DFS we just had a solution set and a visited array. Both of them were kind of arrays, but over here we have a stack and an array. Visited is an array and stack is basically and the stack is basically a LIFO structure. So let's see how we can traverse across this entire graph using topological sorting. So again, let's start with the 0. Let's mark 0 into our visited set, and let's see what is the subgraph looks like for 0. So we check whether and is there any outgoing edge coming out from 0. No, there is no outgoing edge coming out from 0, so we are going to mark it as visited and we are going to put it into a stack and move on. So next element that comes for us is basically 1. We mark it as visited and we check like are there any outgoing edges coming out from 1. No, there are no outgoing edges coming out from 1, so we are going to put it into our stack. Just one thing that to notice over here is that in case of topological sorting, only after covering the entire subgraph for a particular node, then only we are going to put that element back into our stack. We are going to put it only after we have covered all its children nodes. So let's talk about the next element, which is 2. Now 2 we look into we add it to the visited set. We are not currently adding it to the stack. We first check whether what are the elements that are connected to 2, that is what are the outgoing edges from 2. We see that 3 is an outgoing edge to 2. We check whether 3 is already visited. No, 3 is not already visited. So we are going to visit 3, and then we are going to first check whether are there any other edges coming out from 3. Yes, there is an edge coming out from 3, which is 1, but we see that 1 is already visited, so we are not going to take care of 1. We are going to move on. So we check again, is there any other edge coming out from 3? No, there are no more edge coming out from 3. So we are going to stop this subgraph right over here, and we are going to add 3 into our stack now. Right now, we check whether now we are going to move one level up. We are going back to 2. And we are going to check, are there any other nodes connected to 2? No, there are no more nodes added connected with 2. So we are going to stop the recursion for this particular subgraph now, and we are going to put 2 into our stack set. Now we have covered 2, 3. Now we have covered 2. So now we are going to move to the next node, which is 3. But we see that 3 is already added to our visited set, so we are not going to revisit 3 again. What we are going to do is basically we are going to move to the next element, which is like 4. So we are going to put 4 into our visited set. We are going to check what are the outgoing edges coming out from 4. So basically we had 2, that is 0 and 1. But if we see, both 0 and 1 are already visited, so we are not going to revisit them again. We are silently going to put 4 into our stack. Now we are going to move to the next node, which is basically 5. So for 5 we check, we are first going to put it into the visited set. Now we are going to check what are the nodes that are connected to 5. There are 2 nodes that are connected to 5, that is 2 and 0. We check whether 2 and 0 are already visited. Yes, they are already visited, so we are not going to revisit them again. We are going to put 5 back to the stack. Right, so with this we have filled our stack. Now in case of DFS, this was our final solution, that is whatever solution set that we have got. But in case of topological sorting, we have filled up a stack. Now what we are going to do is that pull out all the elements out of the stack. And when we pull out the elements from a stack, they come out in reverse order, because stack is a LIFO kind of a data structure. So our final solution set is going to be 5, 4, 2, 3, 1 and 0. So this is going to be our final solution set. And if we see that, if we are if we put up this order as a final order, it guarantees that for any of the cases where there is an edge from U to V, right, we are not going to face a situation where U is coming after V in this particular topological ordering. Because if you see in the previous solution, we had 0 coming before 5, although there was an edge from 5 to 0. But in this case, 5 is coming before 0 because there is an edge from 5 to 0. And similarly, you can check for any other case. Like see, if there is a edge from 3 to 1, 3 will come before 1. And if there is an edge from 2 to 3, 2 will come before 3. So basically this entire thing is going to be followed. So let's look at the solution for the problem. Let's look at the code for the problem. So now we are just going to code entirely the same thing which we have kind of just discussed. We are just going to put it in the form of a code. So this is how it looks like. First what we do is that we are going to curate a adjacency list. We already know what an adjacency list is. So whatever courses are given to us, we are going to put them up in the form of a adjacency list. Basically, there are two ways to represent a graph. One is adjacency matrix and the other one is an adjacency list. I'm going by the adjacency list way because adjacency list is good in case your graph is sparse. It's much faster. So yeah, I'll go by the adjacency list way. So yeah, like we kind of create this adjacency list, and then we create a stack. We create a stack, and then we start visiting all the nodes that we have over here, starting from 0 to n-1, right? We will keep on. We also maintain that visited array, same that as we have discussed before. So we keep on visiting all these elements and keep on checking whether they have already been visited or not. In case any of them is already visited, we are not going to revisit them. That's what is taken care of by this if else case. Then for all the elements which are not visited, what we are going to do is basically we are going to do a DFS. Now basically, you know, the DFS that we are doing over here is kind of a topological sort only, and because we are passing in the stack over here. So what we do over here is that first we mark the node which is received by this function as you know, visited. Then what we do is that we check whatever adjacent nodes to it are there, and that is what all outgoing edges are there from coming out from that node, and for all of them we are going to, you know, recursively call it for those nodes. And if there is an already visited element or already visited node, we are not going to revisit it, as we have already discussed, right? And after we have covered this entire graph, we are going to put that particular node back into the stack, right? Now in this entire solution, you see that there is one more extra thing which I haven't talked about, which is this Boolean stack array. And you know, I am setting this to true in starting and then setting this to false at end, and somewhere this function is kind of returning a Boolean. Why are we doing this? Now why are we doing this is because you know, this is to detect whether that graph is actually a DAG or not. So DAG, as I told you, is basically a case wherein there is a cycle coming out from you know, cycle that is present, you know, if that the cycle shouldn't be present in case of a DAG. So in case a cycle is present, then basically topological sorting order is not possible. So to handle the handle that particular use case, what I'm doing is that for all the you know, nodes that are coming into picture in the current you know, current subgraph, I am just marking them as true in this you know, you can call this Boolean array. I'm just marking them as true, whatever nodes are coming for me. And for if in that subgraph that nodes comes again somehow, then we can say that there is a, you know, then we can say that the graph is not DAG, that subgraph is not a DAG, because, you know, there is a cyclic dependency on one node to the same node. So if let's say I marked if I marked a particular node as true over here, and we said that, you know, we have already visited this node, and then we have already, you know, visited this node in this particular subgraph, and we see that that node coming up again in the same subgraph, then that means there is a cycle in that subgraph. So in that case, topological sorting order won't be possible, and what we are going to do is to return a false over here. And since we are returning a false over here, we are going to return you know, an empty array over here, because the problem statement clearly says that if the solution is not possible, just return an empty array, right? So for positive cases where, you know, topological sorting order was possible, what we are going to do, as I mentioned before, is that we are going to, you know, traverse across the entire stack and in LIFO order, and you know, we are going to pop out all the elements and put it into an array, and then just return it. Basically, you know, yeah, we are going to return it, and that will be our, you know, final solution for this problem. So I have added the solution link for this problem in the description given below. And thanks for watching this video. I hope you liked it, and stay tuned for many more. Thanks a lot.